Alright, so I'm Colin Hughes. I'm the leader for group 2. We'll be doing the Cloparian experiment. Yes, I looked up the pronunciation, that's what I got. Something with that. So, to start off and do a little background, the Clausius-Cloparian relation is named after Rudolf Clausius and Benoit Paul Emile Cloparian. And the definition I found of this relation is right here. But that's like the technical and hard definition. So to simplify it, basically what that's saying is this equation, you're able to measure something that's not able to measure directly. For instance, enthalpy, you can't measure it directly without pressure and temperature. So this equation is able to do this. So here's the equation that we'll be using for the experiment. You have P is your saturation pressure, T is your saturation temperature, and our lab manual actually uses a different variable for the latent heat of vaporization. They use H, F, and G, I believe. I'm going to use L in this case. V is specific volume, and S is the specific entropy. So I'm going to quickly run through the derivation of this equation. From the state postulate, this is where you start with the equation. And since we'll be using a closed system and constant temperature and pressure, your equation can go to the next step. And I'm not going to get into the Maxwell relation. So with a little bit of magic, your equation can jump down to the bottom. So here's the continuation of it. Our pressure and temperature will be constant. And then you're going to integrate both sides to get, this is the first half of the equation. And then with the first law of thermodynamics, since the phase changes are internally reversible, you can use the first law and it yields that equation, which then you use specific enthalpy and keep going through, integrate, and then finally you get the equation we'll be using, which is the Cloparian equation. And what I read is that the Clausius Cloparian equation is here, and it's when you use the R constant. That's the Clausius Cloparian, but we'll be using the Cloparian equation, which is what I just showed you. So some practical applications of this equation is for meteorology and climatology. What I read, it was actually pretty interesting. Scientists use this equation, they can get information on other planetary clouds in the solar system using this equation. So I thought that was pretty cool. Let's see. Here's a phase diagram, and the equation, the Cloparian equation, you can basically measure, you're able to quantify the latent heat of vaporization between phases. So now to get to the actual experiment that we'll be doing next week, I'll be rolling through the objective, then the apparatus, the procedure, the shutdown procedure, and the expected results. So the objective of this experiment is we're going to use this equation to determine the latent heat of vaporization of water over a range of temperature and pressures. And like we heard earlier, the range of pressures will be from 0 to atmospheric pressure. Then we need to verify our results with the steam tables. This is a diagram of the apparatus we'll be using next week. So I'll go back and forth. Let's see, the setup and preparation. Next week we'll find out if this experiment, if we'll be using boiling beads or not. The purpose of the boiling beads is it provides a controlled boiling. That's what the boiling bead does, but I don't know if we'll be using it or not. We'll find out next week. So then we need a separate flask with 2 inches of water on the hot plate. And we have to make sure the thermocouple is below the surface of the water but is not touching the beaker or the flask. We need to make sure the reservoir has sufficient water, and then we need to leak test the system. Now for the actual experiment, First we need to turn on the vacuum pump, and then we have to plug in the hot plate, and once we plug in the hot plate, we have to wait for the water to boil. And this water is going to boil at nearly zero at pressure, when the pressure is at zero. Like I said earlier, you got to make sure the thermocouple is not touching the beaker. Then we need to log the data after the water boils. Number 5 is a crucial step. We need to close off the vacuum pump to increase the pressure, but if you do it too fast, the water will not continue to boil, which we'll have to restart the experiment. So then we need to check the values of the thermal tables after the water boils. Make sure we're actually doing the experiment right, make sure our numbers are correct. Then you need to open up the air bleed valve and turn off the hot plate. So the shutdown procedure, this is very important too. We're running out of time, so we'll just read those real fast. And here's the expected results. I actually put the wrong graph on there. It should be pressure on the y-axis, temperature on the x-axis, so just imagine the curve the opposite. Grabbed the wrong graph on accident, sorry about that. So our expected results, after choosing 3 arbitrarily chosen pressures, we need to calculate the latent heat of vaporization, which is our H, and then we need to compare all these H's to the tabulated values in the back or of the steam tables. And any questions?